Okay, just for a starter. Got this function R of X. Got a couple of linear factors in the numerator, a couple of linear factors in the denominator, okay? So all I'm asking is, for what values of X is the numerator 0? And for what values is the denominator 0? So give you just a couple minutes, see if you can answer those questions. Okay, I'm going to repeat what I just said for the continuity. The majority of the class is setting X equal to 0. Okay. Now that's a good thing to do, but setting X equal to 0 isn't going to give you 0 for the numerator. It's going to give you -20. And it's not going to give you 0 for the denominator. It's going to give you -6. And most of you have that. Okay. So that's good, because if you set X equal to 0, that does give you information about the graph, but it doesn't answer the question of what values of X make the numerator 0 and what values of X make the denominator 0. Now, some people have it, but give it just a little more thought, and then we'll do it. Okay, well, everybody's on track, and everybody has some of it. So, well, let's just say, over here, it seems like you like as much of the board. What does it mean for the numerator to be 0? We'll take the bathroom and make it. Get a picture out of it. Okay, now I'm just trying to get the board lined up here. So see what I think I'm seeing. Okay, numerator 0 means, well, what's the numerator? I think everybody can identify the numerator. Right there it is. It's above the fraction line. The denominator is below, and everybody knows that. Okay, that means that 2x plus 4 multiplied by x minus 5 equals 0. That's an equation that you can easily solve. You can solve it by inspection, pretty much. By inspection just means you look at it and say, okay, if x is 5, this is going to be 0. Right? That's obvious. And it should be obvious for everything we've done with polynomials. That's how you find the zeros. You put it in factored form and set each factor equal to 0. Okay? Well, it's the same thing with this. It's called a rational function, incidentally. And it's the algebra is probably the hardest in the course when we do this. So hopefully you've worked through the complex fractions and so forth, because it's going to be important. Anyhow, so if x equals 5, we get 0. Now, if 2x plus 4 equals 0, it's also going to be 0. It's not totally obvious what x would be, although you probably can figure out if x is -2, that's going to make this 0. But you can always solve these equations in your head. So what we do is we split this into 2 equations. And of course, we've seen this. This means 2x plus 4 equals 0, or x minus 5 equals 0. And 2x plus 4 equals 0 is an equation we can easily solve. So I'll just put 3 dots here. We solve and we get x equals -2, or x equals 5. Now that gives us some information about the graph, doesn't it? Because if the numerator is 0, then as long as the denominator isn't also 0, the whole thing is 0. If the numerator is 0 and the denominator isn't, we're going to get 0. This tells us that at x equals -2 and x equals 5, we have to go through the x-axis. So this is just totally familiar. Okay, here's x equals -2. And I'll draw this vertical dotted line and just label this one x equals -2 and this one x equals 5. Okay, So that's easy. We know that the graph has to go through this point. So I'm going to put a cross here, an X or whatever, just indicating that the graph is going to go through those points. Now, what happens if the denominator is 0? Well, denominator is 0, that means x plus 3 times x minus 2 equals 0. This means, by inspection, x equals -3 or x equals 2. Okay? Now, I'm going to draw a vertical line for x equals 3 and a vertical line, dotted line, for x equals 2. I don't want to make these lines look like these lines. What I'm going to do is I'm going to kind of make this line a light solid line, and this one also. You'll see why I'm going to do this in a bit. Okay. Now, we can construct the graph pretty much from what we have. There's a little more to it. What I'm going to say for right now is if x is near 2, if r of x is near I guess I'll write it out. 2 times 2 plus 4 times 2 minus 5 over 2 plus 3. Okay, and that takes care of this term, and this term. Now this term is the one that is 0 when x equals 2. So we're talking if x is near 2, and for a reason that I'm not going to totally explain right now, it's this times 1 over x minus 2. And let me just use parentheses there. A lot of parentheses, but there it is. And this equals what? 4 and 4 is 8. 2 minus 5 is -3, so that's -23. And this is 5. Times 1 over x minus 2. Now, why didn't I plug 2 in here? Well, one reason is it's going to give us 1 over 0, and that's undefined, so I really can't do that. But the other is that we see that this is just a transformation of one of the toolkit functions. So my question now is, what transformation of what function gives you -23/5 times 1 over x minus 2? Which toolkit function are we talking about? Okay, so we come to the conclusion that near x equals 2, r of x acts a lot like -23/5 times 1 over x minus 2. Well, what does that graph look like? That says you take the graph of the reciprocal function, which looks like this. Okay. So here's your toolkit reciprocal function. Here. and you multiply it by -23/5. You vertically stretch it by a factor of -23/5. That's -4.6. That means every point becomes 4.6 times as far from the x-axis, and it flips over to the other side of the x-axis. Okay, so they're going to get stretched out about 4 times as long. So it's going to look something like this. And over here, it's going to flip over the x-axis. It's going to end up looking something like this. Okay, so this is like -23/5 times 1 over x. Almost wrote 1 over x minus 2. Actually, I started to write it, so I've got to admit it. Clear that off. See if I can get it one right. Now here's your toolkit reciprocal function. Here's your stretch toolkit reciprocal function. And now, if we replace x by x minus 2, this thing shifts 2 units to the right. Okay, so where's 2 units? Well, that depends on our y scale. I'm going to kind of exaggerate. So it shifts 2 units to the right. I'll just kind of indicate it here. This means that our y-axis will shift 2 units to the right. So we'll just put the new y-axis like here. Okay, so this is now the line x equals 2. If we shift the y-axis 2 units to the right, you get the vertical line x equals 2. And hopefully you're getting some appreciation of why I wanted you on that assignment I gave you the weekend before last to draw all those vertical lines and horizontal lines and everything, so you know what they mean. And I think you do. I think people are in pretty good shape with this idea. Okay, so here we have x equals 2. And that's going to be the vertical asymptote, because x equals 0 is a vertical asymptote for the toolkit reciprocal function. And therefore, for the vertically stretched toolkit reciprocal function. So we move 2 units to the right, and what do we get? Well, we get a graph that's way down here, like this, and it comes down way up here like so. All right. So this means that over here, near x equals 2, this graph has to, at the very least, approach the vertical asymptote like so, because no matter what the rest of the function does to it, the numbers, the magnitude of the numbers we get for the vertical asymptote get astronomical. And they're going to outweigh anything else that happens. Okay, so we know now that we have this asymptote where we're going this way on the left and this way on the right. And this is simply because, excuse me, I might have. Yep. Okay, you can actually see that when I did it, but let's get this over here with way so we can really talk about it. Okay, so we have this information. Okay. That's information about the graph. Very similarly, when x equals -3, then we have another function over here. Okay, so I just say if x is 3, r of x is near, what is it? 2 times 3 plus 4 times 3 minus 5 divided by 3 minus 2 times 1 over x plus 3. In other words, I just took everything in the function other than x plus 3 and plugged in 3. And then we just do the arithmetic. 2 times 3 is 4, and 4 is 10. That's good. So you're going to be easy to multiply by 10. 3 times 5 is 15. That gives us 150 over 1 times 1 over x plus 3. That's just 150 times the reciprocal of x plus 3. It's got a graph. It has a vertical asymptote of x equals -3. And the 150 isn't all that important. It's just there to know that we've got a big vertical stretch here. Okay, big vertical stretch. So this graph, the graph of 150 over 1 plus x plus 3 is going to look like this. All we have is a vertically stretched reciprocal function. You know what that looks like. And it's shifted 3 units to the left. So it's a big stretched out reciprocal function, shift 3 units to the left. And this tells us that near x equals 3, you got to go up like this on this side and down like this on this side. Now there's other stuff that happens because, of course, by the time we get to x equals -2, we got to go through the x-axis. That's kind of close to the x minus 2. So it's going to come down really fast and go through the x-axis. And then what's it going to do? Now, this is problematic as I look at it. But no, it isn't. Never mind. Okay. Bad arithmetic in my head there. It worried me for a second there. I don't think it does. Okay, so we got that much information about the graph. Now that's new. Polynomials don't do that. Polynomials are just nice and smooth from -infinity to infinity, okay? These things, these rational functions where you have denominators that can be 0, those 0 denominators give you vertical asymptotes. And that's really, something you have to deal with. Now, I'm never going to ask you to actually do this arithmetic here, but I did this to convince you that you're going to get vertical asymptotes at these points. And this can be a useful technique sometimes, but it's probably not one you're going to need. All right. And you know what I did over here? I did this wrong. I mean, look at my graph here. Its vertical asymptote goes down here and it goes up here. Okay. So I kind of screwed that up. Not just kind of, really screwed it up. Fortunately, I've got some damp cloth here to fix it with. And the reason I saw that is just because I know that if we came down from here and went through the x-axis, we'd never be able to get back above the x-axis. And I know that when x is a really big number, all these quantities are positive, so it has to be positive. Now, we'll talk about that in more detail, but it's got to go down here and up here. So I did that wrong. All right, but now it's right. So I think this is going to allow us to construct the graph. Now there's one more thing. What's the y-intercept? So I'm going to squeeze that in here. How do you get the y-intercept of any graph? Okay, and I'll make a comment that the majority of the class started by plugging in x equals 0. Okay. Now that doesn't answer the question, what's the numerator? When's the numerator 0 and when's the denominator 0? Because you know when you plug 0 in, you got -20 for the numerator and -6 for the denominator, right? Okay, so I didn't answer the question, but it did tell you what the y-intercept is. So as I said at the time, that was a good thing to do, but make sure you know why you're doing it. Okay, so the y-intercept occurs when x equals 0. So y equals -20 over -6, which is 5/3. Okay, so now we know where the y-intercept is. It's at y equals 5/3, which is approximately 1.7. So now we have y equals 5/3 on our graph. And we can do even more. The one thing we don't have, and the only thing we really need now, is the long run behavior. I do have a problem here. -20 over -5 means we've got to go through the x-axis here. Got to come down from here. How do we get back up to here? That's a real problem, right? I don't think I'm doing anything wrong, but this shows me that maybe I am. I swear I can do arithmetic. Okay. I just need to be more careful about it. 3 minus 5 is -2. And I did 3 times 5 when I did this because I wrote this down really carelessly. So in the first place, this isn't 150 anymore. Okay, that's 10 and that's -2. That's -20 over 1. So this is -20 over 1 times 1 over x plus 3. So our graph for this asymptote has to look like this, which means I've got something else to fix over here. Okay, so we got to come up from down here, and we got to come down from up here if we come to the left. So we got to approach the asymptote this way and this way. So I got them both wrong when I first did it. Got to be careful about that. As I said, I'm not going to ask you to do this and this, although if you want to, if you like the idea, you're welcome to do it. Matter of fact, I think that would be very good. Okay, well, we've got the line y equals 5/3, which turns out to be totally useless. No, it doesn't. No, this is right. That was wrong. Okay, so we got y equals 5/3 here. We know that we have to come up from here and go through the x-axis here. Okay, you look at what I'm doing here. Start down here, go through the x-axis, then we go through here, and then we go up here, right? Can you just off to the side somewhere kind of sketch a vertical line for x equals -3? Yeah, and this is -3. I think I put my negative on that. And vertical line for this, and show me something that starts down here, goes through here, and ends up here. That should be fairly straightforward. Okay, so we worked on this a little. We got to start down here on this side. Notice this green arrow is on this side of the line x equals -3 because it's going to act like this around x equals -3. There's a reason for it. But that's the bottom line is it's going to do that. So it has to start down here, asymptotic to this line, and end up here, asymptotic to this line on this side. And it's got to go through these 2 points. So what's it going to do? Here, so you can see me do it. Oh, wow, it's probably going to be in the way. We're going to come up from way down here. We're going to go through this point, going to go through this point, and then we're just going to come on up like this. Okay. So near the line x equals 2, it's going up like this, right? And near the line x equals -3, it's this function, it's going to go down like this. So it starts down, then over here at x equals 2, it ends up, and it's on the way goes through the two intercepts. Now, I don't know why this thing flipped off of Zoom. It was worrying me a little bit. Okay. So I think we got all that. And okay, yeah. Let's zoom in, or the camera is zoomed a little bit too. Okay, so we have this picture. And now the long run behavior. Plug in, use your calculator, plug in x equals 1,000 here and see what you get. Okay. Okay, so here's the calculation. I'm plugging, okay, we're looking at long run behavior, and what I ask everybody to do is just calculate R of x for x equals 1,000. Okay. Now it's a little strange in the consistency of the results, but they all came out close to what they should have, so we won't worry about that part of it. But what you get is 2 multiplied by 1,000 minus 4, 1,000 minus 5, 1,000 plus 3,000 minus 2, you know that. And if you look at the numbers, you get 2,000 minus 4, 1,000 minus 5, 1,000 plus 3, and 1,000 minus 2. Now, 1,000 minus 2 is 998, and that's really close to 1,000, right? Okay. Would you agree that 998 is close to 1,000? If I said, I'm going to flip a coin, I'm going to give you $998 or $1,000, would you be particularly worried about whether you got that extra $2? You're getting close to $1,000 at the minimum, okay? $2 is pocket change if you have that much money involved. So my point is, this number's close to 1,000. This number's close to 1,000. This number's close to 1,000. And what's this number close to? What's 2,000 minus 4 close to? How many thousand? It's close to 2,000, right? So we can say that this is close to 2,000 times 1,000 over 1,000 times 1,000, right? Now, you need a calculator to figure out 2,000 times 1,000 divided by 1,000 times 1,000. What is it? What do you get if you calculate this? Well, let's think about it. What's 1,000 divided by 1,000? 1. What's 2,000 divided by 1,000? So we get 2 times 1. Okay. And my point is, if you understand the numbers, and if you look at this expression, if x is a really big number, then this number here is going to be twice as big as this number. And this number here is going to be about equal to this number. And we're going to end up with 2. Very close to it. If x, the bigger x is, the closer we're going to be to 2. Okay, so this tells us that we have a large positive X, it follows that y equals r of x is close to 2. What does that tell us about the graph? It tells us that if we draw the line y equals 2, we know what happens to the right of this asymptote at x equals 2. We got to start down here. We got to go through this line, and then we have to approach the y equals 2 line. So how does that work? We come down here, we come up through here, and we kind of approach y equals 2 as an asymptote. On this side, well, I'll just write similarly. X is a big negative number. Our x is again near 2. This means that if we're up here, well, we have to approach 2 on this side. So our graph does this sort of thing. So that's an example of a graph that's about as complicated as anything I'm actually going to test you on. Now let's back up and look at a few slightly simpler graphs that I wanted you to see. And I'm not sure. Keeping this, I need a big monitor out here where I can see what I'm doing. But okay, so again, we had our asymptotes here. They go up here, down here. This tells us how to draw the graph once we have the asymptote to the y equals 2 line. And then on this side of the x equals negative 2 line, we have an asymptote here and an asymptote here. It's very straightforward. Okay. Let's turn to a couple of simpler graphs. Let's try this. Now, what's the first question we asked in what we just did? We asked, when's the numerator 0? When's the denominator 0? Okay. So you kind of maybe want to write this down as sort of an algorithm. So first we find zeros of the numerator and denominator. Then the zeros of the numerator, we're going to indicate by dotted lines. Okay. And we don't always have multiple zeros, so we'll kind of put parentheses around the F. Okay, and zeros of the denominator like solid lines remind us that those are going to be asymptotes. And now we know what asymptotes look like, and we've got an idea how to use them in constructing a graph. Then find the y-intercept. Okay. And we're almost done. And then we do the long run behavior with the dotted line. Or arrow. Now we've got to clarify what we mean by all this. And we might not get all that clarified right now. But there we have an algorithm. You make it 1 step, 2, 3, 4, 5 steps, and then get your curve. Okay, for this, well, I'm going to give you a few minutes and see how far you can get. See how you can do just following those instructions. By the time you get down to the last one, there's going to be something you don't know, and you're not actually going to be able to follow that. Theoretically, at this stage, you could follow all these instructions except the last one, but there's some potential glitches, and we'll see how to deal with those. Okay, now you do what I said. You would write this out and do what it says before you write the rest of it out. Most people wrote it all out, and if that's the way you need to see it, just to get the context, it seems to be working for most of you quite well, so it's okay. But I'm going to follow my own advice. The zeros of the numerator and denominator. Numerator equals 0 if x minus 3 times x plus 5 equals 0. Now I know that you can do this just by looking at it, and you know that x could be 3 or x could be -5. I recommend that you write this out because they're not all going to be this simple, and that you reinforce the idea that this means that x minus 3 is 0 or x plus 5 equals 0 with the logic, so that you understand the logic and reinforce your understanding of the logic. It's hard for people to bring themselves to do this, but you learn a lot more if you do. And you get x equals 3 or x equals 5. Denominator equals 0. X plus 1 equals 0, so that x is -1. Okay, so there we have step 1. I'll call this step 1. So right here is step 1, and 1 is done. Okay, now next, we're going to put the zeros in the numerator, indicate those with dotted lines, zeros to the denominator with light solid lines. Then we're going to find the x-intercept with a dotted line for that. So let's just do step 2. And we can really put that together with step 3. It's okay to kind of do these both in one step. So here we have a graph. And the zeros of the numerator are going to be indicated by dotted lines. What are the dotted lines? The lines x equals 3 and x equals 5. If you haven't written this out, you haven't reinforced the idea that you have the lines x equals 3 and x equals 5, even though you probably, and from everything I see, you remember to put them down. You want to write it out. It reinforces, you remember it better. You have to do less review for the test, and you end up doing better on the test. Okay, so anyhow, and I said x equals 5, x equals -5. Okay, so x equals -5, put that here. And x equals 3 is not going to be quite as close to the y-axis. It's going to be on this side. So here's x equals 3. So there are the vertical lines, x equals 3 and x equals 5. And here's where those lines cross the x-axis. Those are going to be our x-intercepts. Zeros are the denominator. We're going to write as light solid lines. Okay, so 0 is the denominator. Well, that's just x equals -1. So I'm going to write that as a light solid line. And it's -1. I said -1. I thought -1. Something in my brain circuit made me do what I did. Here's a line x equals -1. And that's going to be an asymptote, vertical asymptote. Now, long run. Here's what gets a little bit trickier. We'll call that, oh yeah, find the y-intercept. Okay, well, the y-intercept x equals 0, so y equals my function 0 minus 3 times 0 plus 5 over 0 minus 1 equals 15. So we're going to have a y-intercept at y equals 15. Now, does everybody agree with me so far? Okay, people pointed out bonehead mistakes on my part. I put a -1 here. I'm looking, never mind. I don't have any excuse. I put a -1 here. It's a +1. I was looking at that. And I got a +15. Should have gotten a -15. So we had good teamwork there. A couple of you got me straight on this, and it's much appreciated. Okay. So now I've got the y-intercept. So I want to mark the y-intercept. Okay. So I got to go through these points, and I've got to have vertical asymptotes on a vertical asymptote here. Maybe, well, we'll see. Okay. Before we start constructing the graph, we want the long run behavior. Well, if x is a really big positive number, it's like we have numerator is pretty close to x times x. Denominator is pretty close to x, right? So we have a big number here, a big number here, and an equal, more or less equally big number here. And all three of these numbers are pretty much the same. It's going to leave us a big number. This big number is divided by this one, but this one is left. So that x is going to get really, the value is going to get really big, okay? It's like big times big divided by big, and that equals big. Okay. Now, if it's a big positive number, this number is positive, this number is positive, this number is positive. As soon as x is bigger than 3, all three of these numbers are positive. So if x is 3 billion, well, no doubt that all three of these are positive, right? And a big negative number, well, if x is a big negative number, all three of these are negative. We have a negative times a negative over a negative. Well, that's 3 negatives. Let me use parentheses. Okay. This means that on this side, we have a big positive x. And on this side, we go to a big negative x. All right. So how's this going to work? Well, I'm going to tell you, see how this is an example. You think about it. How am I going to start down here, go through here, and what's going to happen at x equals -1? I'm going to have a vertical asymptote, right? Can I go from here through here to a vertical asymptote at the x-axis? Yeah, I can come down here. I can come through here. Then I can approach this as a vertical asymptote. So that works out. Now, how am I going to start with a vertical asymptote on this side of x equals 1, go through this point, and then go on up? Well, it's pretty easy to do that. I just start down low. I can't start high because I can't get from here down to here without going through the x-axis. And the only places I can go through the x-axis are for the numerator 0. Okay, and that's here or here. I can't go through the x-axis between here and here. So I can't start up here and go down to this point. I've got to start down here and come up to this point. So I do that. And I come through here and then I go on up. Okay. Now there's a little more. And had for the assignment long division assignment. So I can work that. One more thing about this graph, and that is at R of x at R of x is this. This is going to help. All of a sudden that voice started getting into my consciousness. That's the lab across the way. They're not across the hall. Okay, so anyhow, R of x is x minus 3 times x plus 5 over x plus 1. We can expand the numerator. That's x squared plus 2x minus 15 over x plus 1. Okay. Now, if I do a long division, I've got x plus 1 divided into here. We're going to get x here. We're going to get x squared plus x. We're going to subtract this from this. So I better put a little minus there and a little minus there just to keep myself honest. And I get x minus 15. Well, x goes into x one time. And I get x plus 1. And I get then a remainder of minus 16, because I put my minuses here. And I get minus 16. Meaning that when I divide this, I get x plus 1 minus 16 over x plus 1. Now this minus 16 over x plus 1 is just the reciprocal function shifted over one unit to the left as an asymptote here. And you see that reciprocal function represented here and here. Okay, so the remainder gives you the reciprocal function and tells you why you have an asymptote here. The other thing this tells you is that when x gets big, well, 16 over x plus 1 gets really small, because if x is big, your denominator is big, the whole thing is small. So this says that as x approaches infinity, the graph approaches x plus 1. So now we take the line y equals x plus 1, and let's just see where that line would be. If that's 15 and that's 5. Yeah, that'd be a line something like this. Here's the line y equals x plus 1. This tells us that the graph is asymptotic to this line, which means that maybe the graph sort of levels off here and becomes asymptotic to the x plus 1 line. And we call this a slant asymptote. And you'll see that in the open math. Now, what I've just laid on you is most of what you need to know about rational functions, which will be covered again in a few days to maybe a week in your pre-calculus class. If you sort out as much of this as possible now, then something that's pretty hard becomes a whole lot easier. Okay. So do your best with the assignment. By the time you get to it in pre-calculus class, you ought to be very good with it. Okay. Okay, there was a question about this x plus 1. Is this the x plus 1 you're talking about? Or this one? Or this one?
Down one.
Well, this one just comes from the function, right?
Yeah.
But here, when we do the division, we got x plus 1 as part of the quotient. Okay. And that means that, okay, again, we got this and we got the 16 over x plus 1. And it's a minus 16 over x plus 1. Now, the minus 16 over x plus 1 tells you that you really ought to have a vertical asymptote at x equals -1, because this is just the reciprocal function shifted, well, vertically stretched and reflected, and then shifted one unit to the left. So there's that. But this x plus 1, and we've got too many x plus 1s in here. That's just coincidence of the way the functions came up. But this x plus 1 here corresponds to this x plus 1. Okay, has nothing to do with the denominator being x plus 1. It's just a coincidence, and I'd avoided that if I'd been smart, but I didn't. Okay, so This thing here is your slant asymptote. So the graph has to approach this on both sides. I didn't draw it quite that way because I sketched the graph before I did the slant asymptote. Partly because I wasn't sure I was going to get time to do the slant asymptote. Okay, so there's this. This comes out of the division. Okay, comes out of the quotient. Now you're going to see it in open math when you get to it. And hopefully, having seen it here, it'll mean a lot more to you when you see it there, and you'll be able to sail right through it, or at least work through it without too much difficulty.